6.2, we are looking at another method of determining volume using our integral techniques. So we have used already slices, discs, and washers. And now another one is called shells, the cylindrical shell method. All right, so a little background. First, let's talk about a cylinder. Okay, we have this cylinder. Alright, and if I were to, cut this cylinder right here and then unroll it, what shape would it be? So if we like cut something like, think about I wish you could see a sheet of paper rolled up as a cylinder. If you unroll it, it is a sheet of paper, which is a what? A rectangle. If you cut this and unroll it, what you have is a rectangle. Alright, so that's cutting the jagged edges. We can obviously cut it with a straight edge, so it would just be a perfect rectangle here. Alright, so the length of this rectangle is this right here as it unrolls. It is the circumference of the circle. That is the length of the rectangle as it's unrolled. So the circumference of the circle is the same thing as the length of that rectangle. And what about the width of this rectangle? Or you could say the height is the same thing as this right here. It is the height of this cylinder. So as that cylinder is unrolled and makes now like a two-dimensional kind of shape, it is a rectangle with length that is equal to the circumference of the circle of that cylinder, and whose width or height is equal to the height of that cylinder. Alright, so if this cylinder has a radius r, then, and height, let's just say height h, then the area of that rectangle, or the area, we can say the surface area of that cylinder, which is the same thing as the area of that rectangle, is equal to the length, which is 2 pi r, because it's just the circumference of that circle, times the height, which is the height of that cylinder also. So this is the area, the surface area of that cylinder. Alright, so now that we've got that out of the way, so here is an example of using this cylindrical shell method. Alright, so we're going to take this region right here, the region that is enclosed right here. We're going to rotate it. You could rotate it around whatever, but this particular problem or example rotates it around the line x equals -1. So it's not rotating around the x-axis or the y-axis, it's rotating around this axis, the axis of the line x equals -1. And you can see that much better over here. Alright, you can see that it almost looks like a jello mold or a bundt cake or something. And it's rotated around there. Alright, so that's what we're trying to figure out the volume of. And we're going to use the cylindrical shell method to do it. Now you could also do probably like a washer method, and that's fine. The cylindrical shell method can be simpler sometimes, and I think this is probably an example where it will be simpler to do that, even though you could use the other thing too. All right, so what we're going to do is think of it as like doing a bunch of cookie cutters. So like we're cutting out that, and then we're cutting out one next to it right here, and another one. Sorry, I'm just bad illustrator. Cut out another all the way down until you cut out all these increasingly wide cookie cutter things of this shape. All right, so here, let's just take a typical cylinder. Typical cylinder will be this right here. All right, where we're going to do this, just to make it look cylindrical. Okay. So this is a cylinder, a typical cylinder, and it's an infinite number of cylinders that are going to be like that. You know, start from here going this way, and here going this way, like that. All right. So what we're wanting then is the surface area of that cylinder integrated from something to something else. All right. So remember, the surface area for the cylinder is equal to 2 pi r times h. Well, we want it to be in terms of the axis over which we are integrated. So it's going to be 2 pi r of x. So, like, in other words, the radius as a function of x times h of x. That's the height as a function of x. So what is the radius of this cylinder? What is this radius right here? It is the difference between this x-coordinate and this x-coordinate. That's how far that is. It's the difference between these two x-coordinates. Well, what is this x-coordinate? It's got to be in terms of x, and so this x-coordinate is just x. So it's like if we're doing this parabola right here, this parabola is y equals 3 minus x squared. Sorry, 3x minus x squared. Then the x-coordinate on that parabola is just the x-coordinate on that parabola. In terms of x, it's just x. What is the x-coordinate here? The x-coordinate here is -1. Everywhere on this line, the x-coordinate is -1. All right, so the difference in these x-coordinates, in other words, the radius is equal to x minus -1, or we would rewrite it as x plus 1. That is the radius. All right. Now, what is the height of that cylinder? The height of that cylinder is the y-coordinate. But I don't want anything in terms of y because I'm integrating over the x-axis. So the y-coordinate there is the same thing as this. It is 3x minus x squared. In terms of x, the y-coordinate is always going to be 3x minus x squared on this parabola. So the height is 3x minus x squared. And so I'm going to integrate this whole thing, this thing. Gosh, what is going on here? Okay, I think we got the screen fixed. All right, we're integrating this whole thing right here, but all in terms of x. The integral is going to be 2 pi times r of x. R of x is this. 2 pi times x plus 1 times h in terms of x, which is this right here. So times 3x minus x squared. And we're integrating that beginning here throughout where that parabola stops this region right here. So it's from here to here, where this parabola, where this region is enclosed on the x-axis. And it's enclosed beginning at 0 and ending at 3. And that's the x, obviously. So this is the integral we're trying to compute. And you could move the 2 pi outside of the integral, and you could distribute that and do the power rule to do it by hand, or you could do it in the calculator. And that's all good. So, but getting it set up is the hard part, so I'm just going to stop there at where we work on getting it set up. All right, here's a second example. The region bounded by the curve y equals the square root of x. Okay, hopefully we know what that looks like. The x-axis and the line x equals 4. Let me draw that. The curve y equals the square root of x. Looks something like that. The x-axis, this is the x-axis, and the line x equals 4. That's a line going through the x-axis at 4. So it's this region here. All right. So it is this region here, trying to make a pretty decent drawing here. And we're revolving it around the y-axis. This is the y-axis. It's revolving it around this axis. So something like this. This is the region that we're making. All right. So again, we might be able to use, I think we could use the washer method here. Where we're doing like washers or donuts that are like that. That's fine. But the other way to do it is with these cylindrical shells that we were talking about. So we're going to do that. All right. One key to doing this, and I really want to harp on this, is that whatever axis you're revolving it around, in this case it's the y-axis, we're revolving it around that. It could be the x-axis, it could be the line y equals 2, it could be the line x equals -5, it could be something, anything like that. But the cylinder needs to be drawn parallel to that axis. So let's just say I'm making my cylinder right here. So here's my cylinder. My typical cylinder. All right. So that's why. So notice the cylinder is. I'm drawing the line parallel to the axis of rotation to make my cylinder. That's one of the keys. All right. What is this radius? What is this radius? It is the difference between these two x-coordinates. What is this x-coordinate? This x-coordinate, as far as this curve that's making this region is concerned, is the x-coordinate of that curve. Let's just call it x. And the y-coordinate is the square root of x. So this point is the point x, y, or x square root of x. Because that's what y is on this curve. So the radius, and what is the x-coordinate of this? It's just 0. So it's just x minus 0, so it's just x. So the radius in this case is just x. What is the height? What is this height? This height is the y-coordinate. The height is the y-coordinate, which is just the square root of x. So I'm doing the integral then as this curve marches along, as it marches along this region from what to what to enclose that region. Starting here, ending here. So it starts at 0 and ends at 4. Remember the surface area of that cylinder is 2 pi r as a function of x. It's like the length of the rectangle times the height as a function of x. That's like the width of the rectangle. Okay, so that's going to be, I'm going to go ahead and put my 2 pi outside of here, just because I can. And the radius is a function of x, it is x. And the height is a function of x, is the square root of x. And that is the integral that I want to compute. You can do it in the calculator, you can do it by hand. If I want to do it by hand, I would just realize that this is the same thing as x times the square root of x is the same thing as x to the 1/2. So this is like x to the first times x to the 1/2. You add the exponents. 1 plus a half is 3/2. So I'm integrating x to the 3/2. And I would do the power rule. That would become x to the 5/2 over 5/2, or in other words, times 2/5 from 0 to 4. Don't forget though, I've also still got this 2 pi outside of here as well. And plugging in the 4, plugging in the 0, taking the difference, and getting my solution by hand that way. Again, you could also use your calculator. So the main thing is getting the problem set up correctly. Here is another picture. This is the same problem we just did. It's just showing the picture in the book in case this might be a good picture to look at to help you visualize what's going on, including an overhead view right here of the cylindrical shell that is coming through this solid that would be created by revolving this whole thing around the y-axis. All right, next example, example 3. You may think, well, this is the same example. It almost is, except instead of revolving it around the y-axis, this time I'm revolving it around the x-axis. So I've got this still the same region, but instead of revolving this way, I'm revolving this way. Alright. This y is the square root of x. It goes from 0 to 4. Alright. And what we're revolving around the x-axis. Like that. All right, so we could use the disk method. That'd be pretty simple on this problem. Maybe even other methods, but I think it tells us to use the shell method. So that's what we're doing, try to get a good feel for the shell method. So if I'm revolving around the x-axis, then my cylinder needs to be parallel to the x-axis. So this is going to be my cylinder. All right, this is my cylinder. Okay, I know it's an ugly cylinder, but it's a cylinder. All right, what is the radius of this cylinder? The radius of this cylinder, I'm going to draw it right here. What is that radius? It would be better to draw it over here. You can see much better what's going on. Okay. What is the radius of this cylinder right here? It is It is the difference in the y coordinates of these 2 points, of this point and this point. That radius is the difference in these y coordinates. All right. I'm going to be integrating this way, by the way. So these cylinders are growing this way. So I'm going to actually be integrating over the y-axis. So I want things in terms of y in this problem because of that. So if I'm revolving around the x-axis, I'm going to have things in terms of y. If I'm revolving around the y-axis, I'm going to have things in terms of x as far as the cylindrical shell method is concerned. All right. So the y is just the y coordinate. What is the x coordinate? Well, if I take this and I solve it for x instead of for y, square both sides, x would equal y squared. So the x coordinate as far as y is concerned is y squared. So the radius here is the difference in the y coordinates, which is just y minus the y coordinate here is 0. So the radius in terms of y is y minus 0, or just y. What about the height? What about the height of that cylinder? What is this height here? This height is the difference between these x coordinates. The difference between these x coordinates. What is the x coordinate here? It is 4. What is the x coordinate here? We've already said it's y squared. So the height as a function of y is going to equal 4 minus y squared. So it's the difference in these x coordinates, which is 4 minus y squared. So now I can do my integral. The integral is going to be, I can put my 2 pi outside of here, and it's going to be r of y, which is just y, times h of y, which is just 4 minus y squared dy. Now what am I missing? My limits of integration. I may have to do a little work here to figure out what those are. In other words, as these cylinders march this way, what are they going from and to on the y-axis? They're starting at 0, and they're going to this point, which I don't really know off the top of my head yet. What I need to do to figure it out is it's where this curve crosses this line. So I need to set those equal to each other and solve for y. So it's where this is x equals y squared, and this other thing is x equals 4. So if I set y squared equal to 4, y will equal plus or minus 2. So this would be, it would go to 2 then. So it would just go to 2 on the y-axis from 0 to 2. And that integral would compute the volume of that solid. Again, you can do by hand, just distribute the y through the power rule, or do it in your calculator. You can do that too. And that's really it for the cylindrical shell method. Here's a summary if you want to read it of the shell method. Good luck with 6.2.